So that's a truly amazing quality of graphics for a mobile device. Let's take a little drive through here, explore the environment, see the nice quality reflections of the water of the dam floor. You see the indirect lighting and special effects, the God rays in the background, the light shining through the atmosphere. So really this is virtually indistinguishable from the desktop gaming experience, truly capable. And this is all running on Tegra K1 development platform, running under Android. We pull up the Android menu here. You can see it's fully integrated with Android. So it's very exciting. Thank you very much. Let's go back to the slides. Okay, so Tegra K1 allows a whole bunch of new experiences for handheld and embedded devices. Besides gaming, which I've just shown you, Tegra K1 was all over the recent Google I/O conference. I showed you the gaming, which is part of the new gaming environment on Android. We're also very involved with Android TV, computer vision on a tablet, the Tango project where you can capture 3D information with a tablet. We're in Chromebooks. We're the first Android Auto platform, and we're also the first development platform for 64-bit ARM with Android, the Android L release. So we're really enabling a great breadth of GPU computing on Android everywhere at Google I/O. So this is a truly impressive platform, and we built a truly amazing development vehicle for it. Jetson TK1 is what we call the first mobile supercomputer for embedded systems. We have Tegra K1 on it, and all the other peripheral connectors, memory, and all the other pieces, so that you have a fully functional computer on a board. So it's a mobile supercomputer. This has 192 CUDA cores. CUDA 6.5 offers support for ARM and development, a bunch of tools, SDKs, and libraries that allow you to develop applications on this platform. And this is 326 gigaflops on a very small mobile chip. It's really a tremendous achievement. And you can get hands-on experience with this here today. And it's also available in e-tail. You can order one. I don't know the Japanese price, but it's very cost-effective, very excellent entry into GPU computing and development. So one other topic I'd like to talk a little bit more about is machine learning. And machine learning is a pretty old branch of artificial intelligence, first explored maybe 50 years ago. And the idea is that computers can, on their own, learn from data, from information that you present to them. And the best way to be able to do this is unsupervised learning, where the computer program will go through a whole sequence of training data, for example, images, and figure out what can be recognized from it, figure out different classes of things that it can identify. So just like humans, we're born without the ability to identify and recognize specific kinds of objects or animals, but we learn over time as we experience our life. You want to have a computer program that's doing machine learning be trained on a set of images and learn to recognize a person or a dog or a cat very effectively. This is very hard to do, though. So this is, we're at a very special time in the history of machine learning, because there are a few trends that are converging, things that are happening at the same time. The first one is there's an explosion of data I mentioned that earlier. Just a few years ago, there were approximately 300 million images being uploaded to the internet every day. And today, probably by the end of this year, there'll be close to 2 billion images uploaded per day to the internet. And all of this is just people's pictures, and they're unclassified. You don't know what's in those pictures, but you would like to be able to figure out, recognize faces, recognize people, like recognize objects, like show me a bunch of pictures of cats, for example. There's also a study in deep neural networks, which is a approach for machine learning, and the growth of GPU computing, the explosion of parallel pervasive computing. The three of these things together are enabling a real explosion in machine learning. So a while back, Google, in Google Labs, built a project called Google Brain out of 1,000 CPU servers, over 16,000 cores, spent quite a bit of money and quite a bit of power, over $5 million, to build a deep learning system that they were able to train over the course of many weeks to recognize a variety of features in images. So there was considerable excitement about just scaling up to this level and being able to do that. Sometime later, Stanford AI Lab was able to duplicate the performance in terms of recognition quality of Google Brain with a much smaller substrate. So 3 GPU accelerated servers, roughly the same number of cores in 12 GPUs, and about 1/150th of the power and much lower cost. So we really see machine learning becoming pervasive, getting much more broadly applicable. And another example of this is ImageNet, which is a very large collection of images that are commonly used as a baseline for machine learning training. There's a challenge that happens every year where people write their own programs to compete with other people who are trying to demonstrate that they can recognize features in image. And just last year, more than half of the teams competing in this effort were using GPUs. So you can really see that this leverage, this advantage of highly parallel computing is something you can't ignore. It's going to revolutionize machine learning. So you can see this by the fact that many large companies are using machine learning for production, for real products. And there's a lot of important research going on in universities in this area, so the field is moving very, very rapidly. There's a very broad collection of use cases. I just mentioned the image classification, but pretty much any situation where you have a large volume of complex data and you want to extract some meaning from it, machine learning is going to be the way to proceed. It's the only way we can deal with that scale of data. So I think this is a very exciting development. Next, I'd like to